So we finished up parametric and now we're going to start on polar. So polar to me is just the prettiest way to graph anything ever. We're going to have flowers. You can ask your girl to prom. I mean, with the bouquet of polar graphs. I mean, it's just okay. So we're going to start with some of the basics. We're going to get some slopes, some tangents at the pole, kind of trying to sketch a little bit, converting back and forth. Just we're going to start with some pre-calc first and then move on. Okay, so polar graphs. Polar is no longer like in terms of x and y, it doesn't have like a parameter. It's all in terms of a radius and an angle. So basically, like at some angle, maybe like pi over 4, how far do I move out? Maybe we went out 3. So this would be like 3 pi over 4. So r is that directed distance, which is basically a radius, okay? And theta is the angle. You always kind of go counterclockwise, just like the 0, the pi over 2, we move counterclockwise, okay? And here are just kind of some graphs for us as we look. So we've got an angle with a directed distance, and then that's how we would get this point would be my r theta. So we need to know these conversions though, if we have going on, that r squared is the same as x squared plus y squared. So kind of look at this. If this is, again, this r theta value, this line right here is your y value, and this would be your x value. So here's your angle going on. So r squared equals x squared plus y squared. That's just the Pythagorean theorem. Then I know that, hey, the cosine of theta is, here, let's write this out. So, TOA. So the cosine of this theta is the adjacent over the hypotenuse. So here I can see the theta is x over r. And then we basically just want to get it in terms of x. The sine of the theta is the opposite over the hypotenuse. So the y over the r. And then we can solve for y. And the tan of the theta would be opposite over the adjacent. We don't use that one as much. So in polar coordinates, we do not have unique points. Like points can be the exact same with looking at different polars. So I could have this angle of 0 and go out 1 for my radius. Oops, sorry, I just did that backwards. My angle of 0 and go out 1 for my radius. I could also face pi. So if I'm facing pi and go back 1, and I'd still be right here. I could go to 2 pi and go to 1. So there are an infinite amount of polar points that will get you right here. So polar points are not unique. And then the pole is basically when you just stay at the origin, it's any angle, but your radius is 0. So you don't go anywhere. And that's just kind of what we thought. Okay, so let's look at this right here, and I want to, let's graph this first. So this is in a rectangular form. I can see it's a circle where I am centered at 0, 3. So 1, 2, 3. There's my center. My radius is 3, so I'm going to go out 3 in all directions. And have a circle. So that's kind of thinking back for what that would look like. Okay, so let's put this now into polar form. So I'm going to FOIL out that part right here. that perfect square. And then I have x squared plus y squared minus 6y. The 9's cancel. So x squared plus y squared we already know was r squared. And y we know is r sine theta. And just a review, that's from this right here. Okay. So now I am going to put this together. So that. And I'm going to factor out an r. Now I have a zero product property, so I can set each of those equal to 0. And r equals 0, that is, again, just at the pole, so we're going to ignore this one, and we're going to focus on this graph. So solve for r here, and let's go look at it. So let's plug in a theta of 0. So sine of 0 is 0. What about pi over 2? That's 1 times 6. And then that's going to get me, it's going to keep going back and forth, so I need to get something in the middle of those two, so I'm going to go to pi over 4. So 6 times radical 2 over 2 would be 3 radical 2's. And as I move out, let's just kind of talk about this really quick. If I go 1, 1, what is that directed distance here? What is that radius? So this would be 1, this would be 1. 1 squared plus 1 squared equals that line squared. So 2 equals x. That is a radical 2. So if I went out 2 and 2, and I talked about that directed distance, that would be 2 radical 2. So this one wants me to go out 3 radical 2. So I'm going to go 1, 2, 3, and 1, 2, 3, and get right there. So here I can see as I am going along that I am getting a circle. Okay? The exact same one. Math. Okay, so slope and polar is you kind of have to first get to a parametric. So my first step is to turn those equations into a parametric form using that r cosine theta and r sine theta. Then 2 and 3 is just like parametric. So a horizontal tangent and vertical tangent are just like parametric. The trick is that we just have this extra step that we have to do first, and it's sometimes a lot of work. All right, let's do one. The slope of the tangent line, where this is my r, at pi. So I first have to use these guys. Okay, this is the harder form. Here is my r. To plug in. So I plugged in what my r was. I substituted that in. Now it's up to you if you want to go ahead and take those derivatives, or if you want to first try to simplify in any way, but I'm going to leave them like that as I take the derivative, because if I put them together, I'm still going to have multiple rules. So here I can see I have this product rule. So I'm going to find my x prime. I have my first times the derivative of the second plus the second times the derivative of the first. Yeah, I'm going to just clean that up a little bit. Okay. So then I know I need to evaluate that at pi. Let's go ahead and get the derivatives just down, and then we'll put it all together, okay, so we can see a little bit more. So let's go find y prime now. First, second. First times the derivative of the second plus the second times the derivative of the first. Clean that up. Not really much else you can do. So let's just talk about what dy dx would look like now. I know that I'm going to put my y prime here and my x prime here. I'm going to go ahead and rewrite those because I don't like starting with the negative if I don't have to. So there is the first derivative. And then I can find that first derivative, evaluate it. It said, oops, not when x, but when theta equals pi. That would be 2 times -1 squared minus -1, 0. 0 minus 4 times 0 times -1 gives me 3 over 0. So this is undefined. So this is actually going to give me a vertical tangent because the denominator is 0, but the numerator is not. Okay, let's try another one. This one says, find the points, the polar points of a horizontal tangent. So if I'm looking for a horizontal tangent, then I am looking for where the slope is going to be 0. So I want 0 over not 0. So let's see. X of theta is r cosine theta, and y is r sine theta. So let's take our derivative. First times the derivative of the second plus the second times the derivative of the first. Okay, let's go ahead and get our y. First times the derivative of the second plus the second times the derivative of the first. So I know that overall my slope looks like this. So if I'm looking for horizontal tangency, then I am looking for where the denominator equals 0, but this does not equal 0. So let's go set the denominator equal to 0. So I'm basically trying to find where cosine, so I can cancel out those a's, cosine squared equals the sine squared. I'm going to kind of look. I know cosine equals sine at pi over 4 and over, well, the 5 pi over 4, but that's past a pi, so I don't want that. But then I know that this is just the opposite, like the radical 2 over 2 and the negative radical 2 over 2. These are just the opposites, but when I square them, they would be the same. So I know that this is going to occur at that pi over 4 and at the 3 pi over 2, or 3 pi over 4. Oh my gosh. Do you know what? Are you guys yelling at me? I want horizontal, not vertical. I am looking where this is 0. This is not 0. Oh, okay. So we just want to make sure that when we solve here, we don't get those now. Okay, so let's go find for horizontal where this top one is 0. That's okay. That was good practice for us to solve this. That was good for us, right? Okay, so let's go find where this guy equals 0. I think I accidentally, that should be a times, that's why. This is a times. Okay, so when I have two things multiplied equaling 0, then I can set them each individually equal to 0. Again, we're looking between 0, including 0 up to pi. So basically, I'm just looking, where does sine equal 0 and where does cosine equal 0? So at 0, and then again at pi, but we're not including it, and then at pi over 2, and then 3 pi over 2, but then we're past it. So here is where I would get a 0, and then I just have to go check that it is not 0 as well. So these are where we equal 0, and then they do not have anything in common, so we are okay. So I know that these are the two thetas that I am looking for to plug in. Okay, so these are where a horizontal tangent occurs. And we basically found these are where a vertical tangent occurs. And they do not share anything, so that is good. If they shared something, then it would be at rest. It wouldn't be a horizontal or a vertical. Okay, so let's look at what part A is asking a little bit more. It wants me to find the polar points here. So my polar points, I'm going to use my equation, which was r equals a sine theta. Okay, so here, if I plug in my 0, I get out 0. So my first point is 0, 0. And if I plug in my pi over 2, I get out a times 1, which is a. So my a pi over 2. So these would be polar points. Polar points, you use the polar graph. But B says to find rectangular points. So to find rectangular points, I have to use the x equals equation. And I got to go back to what the x was. X was a sine theta cosine theta. And the y equals equation. So y was a sine theta, sine theta. So now I have to plug in those points, or those theta values. So theta kind of x, y is what we're looking for. So we need to look at 0 and at pi over 2, what we get out. So plugging in a 0 here, I can see I get 0, and over here I still get 0. So this would be 0, 0. But this is in terms of x and y. Remember, these are in terms of r and theta. So let's plug in a pi over 2. So that gives me 0 here. And then that would be a times 1 times 1, which is a. So 0, a. And those would represent the exact same points. They're just written a little bit differently. So on here, think about it. We're facing pi over 2, and we go out to a. So that's where this point would be. Here, I just want to say I go 0 on the x and up to a on the y. And you see how that's the exact same point. It's just written a little bit differently in terms of x and y, or in terms of r and theta. Okay, so the next one, what is the slope of the line tangent at theta equals 0? Okay, so when I want slope and I'm in polar, we've got to do a lot of work, okay? Do a lot of work for slope, okay? So many times kiddos want to just go find r prime. No, that's going to tell us something different. We will get to that, but that is not slope, okay? That's the rate of how fast the r is moving. It's not the slope, like at that curve. So we have got to go do all that work. Okay, so we want to first get my x. X is r times cosine theta, and y is my r times sine theta. And then we have to go find the derivatives. And then we're going to plug it in the theta equals 0. I want to see if you can get this on your own. I'll tell you at the end, I got 0 over 2, which was 0, and I want you guys to try that. So go ahead and pause, and then unpause and see if you get that. If not, ask me in class. Okay, so the next concept that we're going to talk about is a tangent line at the pole. So a tangent line at the pole is when you set the original function equal to 0 and you solve, but the derivative of that function is not 0. This is a tangent at the pole, and that's going to help us when we go to graph. And we're going to just barely touch on this one right here to look at the graph, and then we'll do some more, okay? So this wants me to find the tangents at the pole. So that r, to find a tangent at the pole, I have to set that equal to 0. So basically, the negative doesn't matter. And I'm saying, where does that equal 0? Well, I know that when I just have this as an x, that when I plug in 0, that would give me 0. When I plug in pi, that would give me 0. 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. All of those, when I plug them in, if that was just an x, would give me 0. So I need to go now and solve for 5 theta, like this was kind of x. So I'm going to divide everything through by 5. So that's where theta would equal 0, pi over 5, 2 pi over 5, 3 pi over 5, 4 pi over 5, and 5 pi over 5 is pi, which is basically the same line as 0. 0 and pi are kind of that same line. So once I start to repeat and then I'm on the same lines, I stop. So this polar graph is going to have 5 tangents at the pole, which is actually a lot. So I'm going to go graph where all of those are, and a tangent at the pole means that it's going to cross through where that happens. Okay? So I'm going to have pi over 5. So hard to do on here. I'm going to have 2 pi over 5.